right, so today is calculating the pH of a weak acid solution. I'm giving you a big hint. We're going to need a rice table. Okay, but I'm going to show you a little trick that you don't have to do a rice table every single time, because you'll see that every single time you have an acid dissociation, the rice table comes out to the same thing, kind of like on the KSP. If you had KSP of 3 particles, it came out to 4x cubed every single time, and so you didn't have to necessarily draw the rice table, you could just write it. So it's kind of like that, only it's not 4x cubed. All right, so let's just jump into it. Rice table, we're going to do the whole shebang this time. We have the, we want to calculate the pH of a 0.1 molar solution of acetic acid, and it gives you the Ka value. If you have a weak acid, you cannot directly take the log of the concentration because it's such little dissociation, you don't actually have 0.1 of the hydrogen like you do on a strong acid. Okay, so that means rice it out. Okay, so we have acetic acid. How do we want to write acetic acid? The organic chemist way or the inorganic chemist way? Inorganic. HC2H3O2 is going to, we're going to do a little arrow because it's going to be in equilibrium. It's going to give you an H plus C2H3O2 minus. So this is 0.1. This is 0, and this is 0. Okay, so it's going to be minus x plus x plus x. So at equilibrium, we have 0.1 minus x, blah, 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 x and x. Okay, you know this is the rice. I don't have to write out rice, do I? R-I-C-E. All right, so our equilibrium expression, let's remind ourselves what it would be this one time. Ka is hydrogen plus the conjugate base over the acid, just so you remember what it looks like. So we're going to plug x in and 0.1 minus x, and that's going to be equal to 1.8 times 10 to the negative 5th. You will probably get the Ka value of acetic acid memorized. They use acetic acid a lot. It's like a common one. Okay, we're going to neglect x because we always want to try that if we can, because it makes life easier. So then we would say approximately equal to 1.8 times 10 to the 5 equals x squared over 0.1. That's easy peasy math, right? X would be equal to 1.34 times 10 to the negative 3. And I would like you to please also always write equals to your hydrogen concentration. Okay? So that is, if you do the math, that is less than 5% of the concentration, so it was a valid assumption. So we could just say less than 5%, okay. So now we'll take the log of that. So let's do that in a different color so we can see it. So now we have the hydrogen concentration, so we'll take the log of that. So negative log of 1.34 times 10 to the negative 3. Oh, let's talk about decimal points. Remember, our decimal points have to match the significant figures in our concentration. The significant figure in our concentration is 3, rather 3. So we need 3 decimal places. Can I finish the answer and then I'll answer your question?
Yes.
So that would be pH of 2.873. Oh, I'm going to run out of room. There we go. Yes, Neelish.
Okay, you always say that they don't test significance or significant figures on the AP test, or you said there will be 1 point. Would the 1 point be like...
Could be.
It could be like a pH question?
Could be.
Okay.
Yep.
Okay.
And in the last year or two, I don't know if they'll still do it, in the last year or two, it's been pretty obvious which one they were testing, because they'll say things like, be sure to use the correct number of significant figures in your answer. Or like, you know how when we were doing kinetics and we had to calculate the value of little k, they would say, be sure to use the correct units. That's a pretty big clue that that's a point.
Okay.
Yeah, so I can't remember all the different places they've tested that 1 point for a significant figure in there. So it's one of those things that if you know to do it, then obviously do it. But it's not, it's 1 point out of the whole test. It's not a make or break. It's really not.
Yeah.
Of all the things that we have to worry about, we talk about it. It's an easy thing for us to refer to when we're doing answers. But if you forget, not that critical. It's 1 point out of the whole test.
Yeah.
Yeah. Okay. Whereas equilibrium's a lot of points out of the whole test. Yeah. Okay. Not only in the free response, but in the multiple choice as well. Whereas it's 1 point on the whole test. So don't get too bogged down. Like if you accidentally put 2 decimal places, it's not the end of the world. But I'm just stressing it because it's an easy thing to stress. But that was a good question. Okay. Let's do another one. This time we have still acetic acid, but this time we have a much smaller concentration. Okay, so I'm going to show you that if you want me to go back and actually write out the rice table, I will. But I'm going to show you that we can do this a lot quicker because we can say 1.8 times 10 to the negative 5 equals x squared over 1 times 10 to the negative 4 minus x. All right, so we are going to neglect x and see what happens. So when I neglect x, I do my math. I'm just going to do my math. Y'all know how to do the math from here, right? So it would be x squared over that 1 point times 10 to the negative 4. So x ends up being 4.25. Not 0.25, 0.2 times 10 to the negative 5, and that is greater than 5%, so not valid. So when it's not valid, we got to keep it in there, okay? And I put this one in there specifically so you could see what it looks like when it's not valid. Because the vast majority of the time, it's going to be a valid assumption because they want the math to be quick and easy. This was in the discussion board in my Facebook group. None of us have ever really seen a quadratic equation on the AP exam, but that doesn't mean they can't do it at some point because it's in the learning objective. So, all right. So then when we put it back in there, we get x squared plus 1.8 times 10 to the negative 5x minus 1.8 times 10 to the negative 9 is equal to 0. When we throw that in our quadratic equation, in our calculators, we get x is equal to 3.5 times 10 to the negative 5th, which is equal to our hydrogen concentration. So to get the pH, we take the negative log. Don't do what I'm about to do on the test. Write it out, but I'm being lazy. And we had 3, again, significant figures in our concentration, so 3 decimal places here. Bam. Okie dokie, artichoke. Go back to the original. It's the concentration, not the Ka value. The original concentration was 1.00. Most likely it was 3 point something, and I forgot to write down those, whatever it was, 3.47. And out of habit, I did 3.5. But it is 3 in the original concentration. 1.00. Okay?
I'm assuming you also got a negative x and just threw that out, right?
Yeah, I don't even write down the negative x because x can't be negative, right? Yeah, x can't be negative. All right, so next one you do. Pausing the video. All right, you should have gotten 4.229. And so if you were to have to do a problem like this on a multiple choice question, which is 100% not out of the question that they might have you do this, you should always expect to be easy math. They're going to pick values that become easy math, so like 0.1 on your concentration or something that's easy to multiply and then easy to take the square root of. So anytime you have multiple choice with math, look for the easy math out of it. I mean, it doesn't necessarily mean it was an easy setup, but they usually pick numbers in there that are like divisible by 2 very easily or that you can ballpark, so just expect easy math. Okay, I know sometimes you would see that and go, I can't do that in my head, but you got to learn to that. I didn't have time in 5th period, so I don't have time today, but tomorrow the lecture shouldn't take very long, and I want to pull up the video, have a small short little video that actually shows you how to estimate in your head pH values or log values. So like if I'm taking the log of 1, 0. If I'm taking the log of 1 times 10 to the negative 5, it's 5. But what if I'm taking the log of 2.7 times 10 to the negative 5? Not as easy because it's not just 5. And there's a way to show you, hey, depending on where you are you going to be 5 or are you going to be closer to 6 or whatnot? Okay. I know how to do it in my head, but I don't explain it as well as the video does, so I'm going to show that. Okay. All right, calculating the pH of, it says polyprotic, but it could also be, should be also diprotic. We said this earlier, all acids dissociate one hydrogen at a time. Each dissociation has its own Ka value, and as each hydrogen is removed, the remaining acid gets weaker. Therefore, each subsequent Ka value is going to be smaller. And as the negative charge on the acid increases, it becomes more difficult to remove that positively charged proton. So the best thing here is to just show you, because this is where I messed up in 5th period. I tried to explain something verbally, and they were like, what? And then when I showed them mathematically, it made a lot more sense. So good thing the recording messed up in 5th period, because I messed it up. Okay. Except for H2SO4, polyprotic acids have Ka2 and Ka3 values that are so much weaker than their K1 that the dissociation can be ignored in terms of the amount of hydrogen that's going to contribute to the pH. Okay? And we're going to see this in a minute in phosphoric acid. We're going to see that only the first dissociation offers any measurable hydrogen to affect the pH. But H2SO4 is a different animal. Okay? If you have 1 molar H2SO4 or greater, then you can just get the pH from the first dissociation. Okay? If you have less than that, then you have to do the second dissociation. Okay? Because it will contribute. So now I'm going to show you what I said to them and explain it. And it will not be asked for on the AP exam, but it could have you estimate. Maybe it wouldn't have you calculate it because it's got it will take the quadratic equation, but they could ask you to estimate it. So before I show you how to estimate it, let me show you how to calculate it so that you understand, because I totally confused them. That's not supposed to be there. I thought that slide got deleted, so ignore that slide. Okay, so we're going to calculate the pH of, did I skip 7? I did. I was like, whoops. We're going to calculate the pH of a 1 molar H2SO4 so that you can see that the second dissociation offers no change to the pH. Okay, so first dissociation, right, is H2SO4 going to H plus HSO4 minus. Okay, and then we don't have to do anything in terms of that other than this is going to be 1.0. When this dissociates, it's going to be 1.0 and 1.0. Does that make sense? Just like when we were doing ionic compounds, if it's a complete 100% ionization, the molarity is the same for the two things that are ionized. Okay? So in this case, pH is going to be the negative log of 1, which is 0. Okay? So then let's do the second dissociation, which is going to be HSO4 going to H plus SO4 2 minus. Okay? So this is 1.0, right? And this initially is 0 and 0. So then we'll do minus X, plus X, and then plus X. So then we have 1.0 minus X, X, and X. Okay? Just kidding. I lied. Dang it, Vanessa. This is not H. I mean, this is not 1. This is not 0, it's 1. Because of that right there. So this is 1 plus X. I apologize. This is what happens when I'm copying from my notes. I'm not thinking, I'm just copying. Okay? So now when we put this in, we're going to have 1.2 times 10 to the negative 2, because that's the Ka value for HSO4, is equal to 1 plus x, x over 1 minus x. Okay? And I'm going to say neglect x here because that makes life way easier. And we have a fairly high concentration of 1. So when I do that, x is equal to 1.2 times 10 to the negative 2. Now my total hydrogen concentration is 1 plus 1.2 times 10 to the negative 2. So now I would take the negative log of 1.012, and guess what that's equal to? 0. So if I'm 1 molar or higher, you see that it doesn't contribute, okay? Because the concentration is too high for the second dissociation to happen, okay? So now let's do the same thing, but we're going to do H2SO4 with a smaller concentration, okay? Does anybody, before I get all this erased, does anybody have a question on what we did there? I want to make sure, especially because I goofed, you understand why this is 1 right here because of that one. Because that concentration is still floating around in the solution, right? Okay.
You neglect the x
Because I always try to neglect x if I can. And 0.012 is definitely less than 5%. So always try to neglect x if possible, okay? And especially on the AP exam, assume that you can neglect it. Yes?
How often do you have to neglect X?
Most of the time. Yeah, most of the time. Most of the time on like KSP and things like that. If it's standard equilibrium pressure, like the KP or KC, then I would question whether I do it. Because then usually they make it pretty easy to make it perfect square. Yeah. If it's a perfect square, don't neglect anything, just perfect square it. Like when we first did the equilibrium expression for KC, there were several that I showed you that were like you could take the square root and get rid of everything. Then don't neglect x if you can do that. Okay? But if it's an acid or a base one, you can or KSP, you can usually neglect it. Usually. Yes.
You won't ever have to use the POLYPROTIC.
I'm not saying never.
No, sorry, no.
Yeah. I'm not saying never. I am saying that to my knowledge and to the people in my network of AP teachers, to my knowledge, we've never really seen it. But the College Board just likes to throw curveballs every now and then. I really generally would be shocked if they put it on there. But I also don't want to send you off to college with never have shown you this. Because some of you, even though you're past the AP exam, some of you will still probably have to take it, depending on what your major is. And I don't want you to say, Ms. Parker never showed me this. Yeah. So some of the few, I don't do a lot of extras that are on the AP exam, but there's some that I feel will help you in college that I go ahead and show you. Yes?
So you neglect x in the denominator and the numerator, where it's like 1 plus x.
Well, when you're neglecting x, you only neglect the minus or the plus.
Yeah.
You never neglect the x you're solving for.
No, I didn't do that.
But if you're neglecting x, you can do it in both places because what we're saying when we say we're neglecting it is that it's so small that from 1 or added to 1, not going to make a difference in our calculations. Okay. All right, so let's do it a smaller concentration now. Okay, and that is same difference, but now we're not going to do the. Are you okay if I don't do the whole rice table here?
Yes.
Okay, I'm going to do maybe I still want to. I'll do the first dissociation, right? So we have H plus in the first dissociation is going to be equal to 0.01. That's also going to be equal to the HSO4 minus. Do you agree with that? Okay, so we're good there. So if I were to take the negative log of 0.01, I get a pH is equal to 2. All right? Now if I do the second dissociation, right? I just feel better writing this out for you guys. So this is 0.01, this is 0.01, and this is x, right? So minus x plus x plus x. So 0.01 minus x, 0.01 plus x, and then x. Okay? And I already told you that this is going to require a quadratic equation, so we already know that we're not going to be able to neglect x here. But 0.01, x is going to be more than 5% of 0.01. Yes?
Did you mean for that x under SO14?
No, I did not. You're right. 0. Okay? So now we have our 1.2 times 10 to the negative 2 is equal to 0.01 plus x. I'm not going too fast, am I? Because last time I did. Okay, so we're not going to be able to neglect. You could probably tell that already by the fact that we have a low Ka and a low concentration. So what x would be equal to is really small, and it wouldn't, you know, like, I mean, it's not going to be a big, huge number. Like if Ka had a negative 7, then you know my x is going to have an exponent around a negative 7, so it's not going to be very much of that, but it's going to be a low exponent now. So I'm going to move up here so I have room. So when I collect those terms, I get x squared plus 2.2 times 10 to the negative 2x, and I'm running out of room, minus 1.2 times 10 to the negative 4 equals 0. So x ends up being 0.0045 for the second dissociation. So now for my total hydrogen, let's go with green. For my total hydrogen, I have to add 0.01 plus 0.0045. So I get 0.004. No, that's not right. Sorry, I'm copying the wrong thing here. 0.0145. So now take the negative log of 0.0145.
Wait, why did you use 0.0045 and not add it to 0.01?
I did right there. This x right here is only from the second dissociation. This is the first.
Yeah, but there's a second 0.01 in your rice table. Like, in the column of, like, in the column of the H ion.
Right here?
Where?
Right here?
Yes. Why did you add that?
What do you mean, why didn't I add that? I did right here, 0.01 plus
Yeah,
x.
that's what that 0.01
Oh,
is.
then.
She's just moving the 0.01 from the first.
Oh,
dissociation to
okay.
the rest table.
I mean, this is exactly what I'm doing, 0.01 plus x right here. I found x to be this.
Okay, yeah. Okay, okay.
1.839. So when our concentration was 1 or above, the second dissociation offered no value to us. But when I start going below that, it does. So what I want to explain to you is they would most likely never ask you to calculate this, but they might ask you to pick it out on a multiple choice question, because they want you to understand that under a certain value that the second hydrogen does offer some hydrogen, which affects the pH. So what you would do is if you saw, hey, what is the pH of 0.01 whatever solution of something that's diprotic, you would figure out what that pH is for the first dissociation, so in this case 2, and it just stopped, it just disconnected. Are you kidding me? Stupid Siri. Not Siri, Doceri. Keep. Okay, that time it kept it. Okay, so I'm going to start that over since the thing played out of me. So what you would estimate is a little bit below whatever you get your initial pH to be. Thank you. Okay? So like if your first dissociation gave you a pH of 2, you know the second dissociation is going to offer a little bit of hydrogen, which is going to increase your concentration, which is going to lower your pH. So you would pick the pH that they selected as slightly under 2. Okay? Or if your concentration was maybe 0.001, you would get a pH of 3, but if it's H2SO4, then you would select a pH slightly below 3. Does that make sense now that you've seen the math? Because I tried to explain that without the math, and they were like looking at me, and then when I explained it, then when I showed them the math, they're like, oh, yeah.
So you said that the increase in H plus lowers the pH?
Yes, because it's the power of hydrogen.
Right.
Yeah, so if you have more hydrogen, you have a lower pH. Right? Because you're taking the negative log. So if you have if the more hydrogen you have, the lower the pH you have. Yeah, it's a negative. Okay? Are we good there? Did y'all like that problem? Because you're going to love the next one. The next one's fun. Okay, this one. Oh, that's saying the same thing. That's probably a better way to say it. Read that. Is that a better way to say it than what I did, or
It's concise.
it's not in your notes?
Yeah, that's not in our notes.
Well, that's what I said. Okay. It's the same thing I just said. Estimate below a 2 if you have lower than concentration. It's exactly what I just said. Okay. This one is fun. Okay. It's H3PO4, which means it has 3 dissociations. What? 3 dissociations. So here's where I made a grave mistake earlier. So I'm not going to make this grave mistake this time. I'm going to write out all the first, the second, and the third dissociation. Okay? So the first dissociation will be H3PO4 yields H plus H2PO4 minus, right? The second dissociation is H2PO4 minus yields H plus HPO4 2 minus, and then the last dissociation is HPO4 minus yields H plus and PO4 3 minus.
Does H2O2 minus dissociates into that? Because you have the 2 minus.
Yeah, I forgot that 2 shouldn't be there. There. Okay? Do you agree with all those dissociations? So basically the product in the first dissociation becomes the reactant in the second dissociation, and vice versa. Okay? What?
Why isn't it 2 minus?
It is too much.
She just wasn't there, she just
Don't
erased
you
the
get
2.
to the third?
Oh, I did the...
Yeah, it's 2 minus there and then 2
Okay, and then,
2 minus there and 2 minus there.
and 2 in the third, right?
On the left side.
Yes.
Okay.
Whatever. I'm not erasing that. Will you open and see what that is? Okay. It's hashtag whatever Wednesday. Oh, okay. Oh, sadness. I have to give up my recycling trophy. Tear. Okay. All right. So those are the 3 dissociations. So that's going to help us as we go through that. So when we're visualizing what their KAs should look like, right? We know what's on the top, what's on the bottom. Okay, because that got confusing earlier. Okay. So let's do the first dissociation. And remember a while ago I told you when you have something like this, the only hydrogen that is going to be contributing to the pH is the first dissociation because it's so small in the second and the third. So we're going to get the pH from the first dissociation hydrogen concentration. Okay? So that's going to look like this. It's going to say 7.5 times 10 to the negative 3 is going to be equal to x squared over 5 molar. I don't know why I put the M in there. It doesn't go there. Okay? That's a giant concentration. Okay? And it's very little dissociation because it's a weak acid. So we can for sure neglect X here. Okay? Because we're... Huh? You don't believe me?
No, I believe you.
Okay. Okay, so then X is going to end up being 0.19 molar, which is equal to the hydrogen concentration and the H2PO4 concentration minus. Do you agree with that? Say yes,
Yes.
because they dissociate 1 to 1, right?
Yeah.
Okay. When we do, excuse me, when we do a rice table, what does our...
Did it stop?
Yes. Hold on. Okay. So whenever we do a rice table, when we have our reactant always ends up being something minus X, right? So guess what? Because these are all at equilibrium, that makes a difference. So our concentration of our acid at equilibrium is going to be 5 minus 0.19. Because that's our X, right? So 4.8 molar is our H3PO4. So I'm going to, because I don't have room to rewrite it. If you want to rewrite it, that's awesome. But I'm going to like put a black box around all of the concentrations it's asking for because I don't have room to rewrite it. On my notes, I rewrote it nice and neat and pretty and said, here's all my concentrations. But I don't have time, I don't have a place to do that. Okay? Okay. Now, before I do this, are you okay with me erasing the dissociations up here? Because I don't have room to, I still got lots to do. If you don't understand what I did just then, or you're struggling, you stop and ask me questions. Do you know why I subtracted the 0.19 from the original concentration? What? Yeah, it was used up. That's the minus x. So I got to minus out the x to see what's left at equilibrium. Okay? So now for the second dissociation, okay, remember Ka for the second dissociation is going to look like this. H plus HPO4 2 minus over H2 PO4 minus, right? Going back and looking at your reaction. So that means I'm going to have 6.2 times 10 to the negative 8 equals 0.19 x over 0.19. Do you agree with me? Yes. What's your question?
Okay. So throughout this whole entire dissociation, the concentration of H plus remains 0.19.
Yes, because you'll see in a minute that x becomes so small that mathematically it won't make a difference. It's
Okay.
going to be like adding
Like
times 10 to the negative 8 to 0.19. So you would have 0.19, whatever.
Okay, so we can just assume that H plus stays 0.19.
Yes,
after the
because
first
it's a weak acid, and it's very high concentration. Any hydrogen after the first dissociation will not contribute. It's negligible to the hydrogen that would affect the pH.
Okay.
Okay?
Great.
All right. So then X, which is equal to HPO4 minus, right, is equal to 6.2 times 10 to the negative 8. Box it, because that's one of our concentrations that they're asking for. Okay? Ready for the third dissociation? And the reason we have to do the third one is because we need the phosphate value. Okay? So, now we're really getting to a small Ka. Let's do third. So 4.8 times 10 to the negative 13 is equal to 0.19, right?
Yes.
X over 6.2 times 10 to the negative 8. So X, which is equal to the phosphate, ends up being really, really small. 1.6 times 10 to the negative 19 molar. Forgot to put molar on that one. Box that one in black so you know which one it is. Now, see, I think that's a fun problem. Yes.
It says calculate the pH too. Would we just, that's just.
Yes. Let's go. That's the last step. Calculate the pH, or was the first step actually? pH, negative log of 0.19. Two significant figures there, so we need two decimal places. So your pH is equal to 0.712. Is that right? Did I do that right? Someone do that. Okay.
721.
721?
I get 721. Yeah.
Same.
Oh, my transposing numbers struck again. I did that at home when I was doing this. I glad I said check it. Okay? So, would they put a problem like that on the AP exam? Most likely not, but that is good math to see what you can substitute and how you can substitute it. So it's a very good exercise in saying, hey, if I calculated it over here, I can still plug it in my next dissociation because it's going to be the one that contributes the most. Okay? Any questions before I erase all that mess? Yes?
So, just to clarify why you subtracted from 5, so you get the 5 molar of the H3PO4,
Uh-huh.
and then you subtract because you get the 0.19.
Because that's your X value. So if we were to do the rice table, remember whatever the reactant is, it always ends up being your concentration minus X, right? And then on the other side it's plus X. So it's because at equilibrium it's always whatever you started with minus X, just like we've been doing all along. Yeah. Okay? Let's keep moving forward. If Doceri will cooperate and not kick me out again. Determination of the pH of a mixture of weak acids. So if I say, hey, I got acetic acid mixed with some hydrofluoric acid, what's its pH? Okay, so only the acid with the largest Ka value, which is going to have the smallest negative number, don't get that confused, will contribute an appreciable amount of H+. Okay, so you would determine the pH of the acid based on the highest or largest Ka value and ignore any of the others. Okay, so of course you know we're going to do an example. So in this example we have hydrocyanic acid or cyanic acid. It's got a really low Ka value, -10, and 5 molar nitrous acid, which has a much larger Ka value. But then it also says calculate the concentration of the cyanide atom that's at equilibrium. Okay, so we're going to take the 4.0 times 10 to the -4 equals x squared, right, over, and y'all, that's not bothering you that I'm just skipping the rice table, right? Okay, over 5. Technically, it should be 5 minus x, right? But it's very big concentration. Our x isn't going to be that much of it, okay? So then I get x is equal to 0.0447, which is equal to my hydrogen concentration. So then I take the pH, negative log 0.0447. I have 3 significant figures, but I wrote down my pH of only 2 decimal places, so someone do it and tell me what the... I have 1.35. I suspect it's 1.34 something.
1.349.
Yeah, so that would be technically right. So that's the first part of that. Then it wants to know what's the concentration of cyanide at equilibrium. Okay, so this time we'll use cyanide's Ka value, 6.2 times 10 to the -10 is equal. What am I going to use for my hydrogen concentration here? 0.0447, because it's going to it's in there with it, right? And then X is for cyanide, and then the concentration of cyanide was 1.00. So that my cyanide concentration is 1.4 times 10 to the -8. Now, if I hadn't just shown you the big phosphoric acid, would you have known to put 0.0447 in there for hydrogen?
Wait, are we sure that the hydrogen concentration whenever we disassociate HCN is less than 5% of 0.0447?
We're absolutely sure.
We are? Okay. Okay.
Yeah. You've got a very, very small Ka value.
Okay.
Very, very small Ka value.
Okay.
Yeah. Yeah. And whenever you're dissociating it, it's going to be so much less that whatever hydrogen does come, is going to be so much less than 0.0447 that it's negligible.
Okay.
Okay? All right. On to percent dissociation. And this is where we're stopping. I know you're so happy. I am. I know these are long lectures, but it's like, it's better to get it all, like, the more we work at problems, the better you understand them. All right. The good news is percent dissociation, easy peasy, lemon squeezy. You take your amount dissociated, basically your X value that you saw for, and you divide by the original concentration and times 100. And that's telling you how much dissociated. Okay? So that's easy peasy. The thing you need to remember when you're looking at something, the more concentrated, the less dissociation you have. Because if you go back and look at that equation, your initial concentration, if you're putting a larger number on the bottom, you're going to have a smaller percent dissociation. If you're putting a much smaller number on the bottom, you're going to have a larger dissociation. So guess what? We'll work a big and a small. Okay. So let's do this acetic acid. This is A. So it'd be 1.8 times 10 to the negative 5 equals x squared over 1. So then x ends up being 0.0042. Oh, it also wants the pH, right? So that's equal to your hydrogen concentration. So the pH, don't do what I do when I show you what I'm about to do. Just write it out, but I'm running out of room. Don't do that on a test. Point the arrow. That's bad. Don't do that. Do as I...
Do as I say, how as I do.
Yeah. So that ends up being 2.376. Oh, just wait for me, because percent dissociation is going to be 0.0042 over 1 times 100 is 0.42%. Okay, then, does everybody have that? Because I'm going to erase it. So that's 0.442%. Then for the next one, 1.8 times 10 to the negative 5 is equal to x squared over 0.1. So x is 0.0013. pH ends up being 2.886. So then percent dissociation is 0.0013 over 0.1 times 100, which is 1.3%. So it went up by 4 times when we went down. One more to work, and then we'll stop. But one thing I want you to be aware of is that we tend to think of weak acids as having super high pHs, like 6 or 7. These are relatively low concentrations of acetic acid, and they still have a pretty good low pH. Okay. And then last one, and then you can leave me forever. Just not kidding, just till tomorrow. This one is, what if I give you the other stuff and want you to calculate the Ka? So I give you that there's a 0.1 molar solution, and I tell you it's 3.7% dissociated. And so this, very quick and easy math, solve for x is 0.1 is equal to 0.037, because I took the percentage out. So then x is equal to 0.0037, which is equal to my hydrogen concentration. So then to get Ka, I write 0.0037. If that's it for H, also it for the conjugate, right? Because of the 1-to-1 dissociation. And then divided by the molarity that they gave us for that, and we get a Ka value of 1.36 times 10 to the negative 4. Any questions on that? Tomorrow we'll do bases.